First, pause the video for a minute and read the question carefully. So the question is about birds striking windows. The birds see the earth reflected on the window and they fly into it. So the researchers did a small experiment to see if tilting the windows towards the earth, so the reflection is the earth and not the sky, would actually reduce the number of bird strikes. So they placed 6 windows at the edge of the wood. 2 of them were vertical, 2 tilted to 20 degrees and 2 tilted to 40 degrees. And the next few months, they observed the number of bird strikes at each type of window. So there were 31 observed strikes at the vertical windows, 14 bird strikes on the 20-degree windows, and 8 bird strikes on the 40-degree windows. So these are the counts of the number of strikes on each type of window. Now, what they're trying to see is if tilt actually affects the number of bird strikes. Just by looking at the numbers, it seems like there were a maximum number of strikes in the vertical window and minimum number of strikes in the 40-degree window. But just by observing that, we cannot scientifically make any sort of conclusions. We need to have concrete evidence that tilt actually affects the number of bird strikes. So our statement is the first thing we need to write down. We'll find evidence that tilting windows down so it reflects the earth rather than the sky will make a difference in the number of bird strikes on those windows. So here again, the variable here is the 3 types of windows that were set up. One was the vertical window, the other was the 20-degree window, and the other was the 40-degree window. So there are 3 categories or 3 types or 3 buckets in here, 3 types of windows. And then we have the counts. We are given 31 bird strikes on the vertical window, 14 bird strikes in the 20-degree window, and 8 bird strikes in the 40-degree window. So we're given the variable, which is the type of window, which is the first row, and the number of strikes or counts in the second row. So this is a variable that is clearly categorical. If we have a categorical variable with the counts given and we need to do a hypothesis test because we are trying to prove something here, we need to do a chi-squared test. And to start off the chi-squared test, we need to calculate the chi-squared statistic, take it to table D to find the p-value, and then finally we make a conclusion just like any other hypothesis test. So the formula that we're going to use, let's just write it down first because that gives us a start. The formula tells us what we need in order to find the chi-squared statistic, which will give us the p-value and hence the evidence or the lack of it to make a conclusion. So let's examine the chi-squared statistic. It's the observed counts minus the expected counts, square it, so that's a square, divided by the expected counts. So we need to first understand what are observed counts and what are expected counts. The counts that we get from the experiment conducted are the observed counts. So observed counts come from the observations of the experiment. Now when we do a hypothesis test, the first thing to do always is to set up the null and alternative hypothesis. So in this problem, we're trying to prove that tilt actually makes a difference in the number of bird strikes. So the null hypothesis in this particular problem is the no difference statement. So what does it mean when we say that there is no difference in the number of bird strikes even if tilt is changed. So what that really means is that the fraction or proportion of counts that fall into each bucket must all be equal. So in the total number of counts, the fraction or proportion of counts on the vertical windows should be 1/3. The fraction or proportion of the counts in the 40-degree windows should be 1/3. And the third bucket, which is the 20-degree window, the probability or proportion should also be 1/3. So this is what a no difference statement really means. The fraction of bird strikes in each bucket should all be the same, which means that the probability that a bird strikes on the vertical window must be equal to the probability that the bird strikes in the 40-degree window must be equal to the probability that the bird strikes in the 20-degree window, which means each probability or proportion must be equal to 1/3. So our null hypothesis is that each proportion is the same and it must be equal to a 1/3. So when you add up all the fractions that you see, there are 3 1/3, so 3 times 1/3 equals 1. So make sure that the fractions add up to 1. In a chi-squared test, the alternative hypothesis is just one statement. No matter what the problem is, the alternative statement is H0 is not true. So the chi-squared test, at the end of the test, will only give us one of the two conclusions. Either H0 is not true, which means we have the evidence to reject it, or we do not have enough evidence to reject H0, which is assumed to be true. So the alternative hypothesis is not very specific as the ones that we've seen before. You just have to say H0 not true. So now we can set up our null hypothesis, and this is how we write down the null hypothesis as we've done before in the various hypothesis tests that we've done. H0, H subscript 0, is the null hypothesis, what is believed to be true. And that is, in this case, probability that the bird hits the vertical window is equal to the probability that the bird hits the 20-degree window is equal to the probability that the bird hits the 40-degree window, and they are all each equal to 1/3. So when you add up 3/3, you get a 1, and that makes a whole. So we have 3 categories that make a whole. Now the alternative hypothesis just says that H0 is not true. So it's a simple alternative hypothesis. No matter what the problem is in a chi-squared test, the only alternative hypothesis is that H0 is not true. So write it exactly the way I've written it here, and that's how you would write down your null and alternative hypothesis. So before you start any sort of calculations in a hypothesis test, you need to set up your null and alternative hypotheses, and that's exactly what we've done. The next thing in a hypothesis test is to set your significance level. The significance level can be any number decided in advance, but we've used 0.05 as our standard. It can be more or less depending on the problem, but let's just use 0.05 as we've done always. Now in the chi-squared statistic, we've seen that we need the observed counts, which come from the data given, and the expected counts. The expected counts are usually not given in the question. That's something that we need to come up with, because we are the ones who come up with the null hypothesis. We use the null hypothesis to set up the numbers which are the expected counts. Now this is how we find the expected counts. The expected counts are based on the null hypothesis. The null hypothesis assumes that all 3 categories must have the exact same number of counts, which means the probability that a bird strikes any one of the 3 types of windows is 1/3. So if the total number of counts, that is 31 plus 14 plus 8 equals 53, that's the total number of strikes. And if we're assuming that the number of strikes should be equal, in this case we just divide 53 by 3, and that would be 17.67, and that's the number that falls into each bucket. So this clearly tells us that what we're expecting is that the number of bird strikes in each bucket is exactly the same. Now you're probably wondering how a count can have a decimal number. I would suggest just leaving it as a decimal number, because we're not really doing a count here. We're just theoretically saying that the number of bird strikes should be the same in each. So you can leave the decimal places alone. So the next step is to substitute all the values that we have. We have the observed number of bird strikes in the vertical window minus expected number of bird strikes, the whole squared, divided by the expected number of bird strikes. Again, observed number of bird strikes minus expected number of bird strikes in the 40-degree window, the whole squared, divided by the expected number of bird strikes, plus the observed minus expected, the whole squared, divided by the expected for the 20-degree window. Now calculate each piece separately. Make sure you have, if you have 3 buckets, make sure you have 3 numbers added together to give you the final answer, which is the chi-squared statistic. This is called the chi-squared statistic. Now each of these numbers comes from each of the categories. So this comes from the vertical window, this comes from the 40-degree window, and this comes from the 20-degree window. And each is called a component of the chi-squared statistic. So we add the 3 components of the chi-squared statistic to give us the 16.11, which is the chi-squared statistic. So each component is important, but we're going to use those components only after we've concluded the test. So once we get the numbers added together, which is our chi-squared statistic, 16.11, that's a number that we take to table D. And the way we use table D is almost the same as how we use table C, which is the t-distribution table. Table D is the chi-squared distribution table. So that's where we go to find the p-value. Now, just as in the case of a t-distribution table, we need to know the degrees of freedom before we can find the p-value from this particular table, which is the chi-squared distribution table. So in a chi-squared test, the degrees of freedom is calculated in a very specific way. What we count here is not the sample size, but what we count here is the number of buckets, or the number of categories. So we have the vertical, the 40-degree, and the 20-degree windows. So we have 3 buckets or 3 categories in our variable. This is our variable, which is the tilt, and we have 3 buckets or 3 categories. So degrees of freedom is the number of buckets minus 1, and that is equal to 2. So what we need to know before we calculate the degrees of freedom is the number of buckets, or the number of categories for which we have counts, and that is 3. So 3 minus 1, subtract 1 from the number of categories to give us 2, which is the degrees of freedom. Now we take the chi-squared statistic along with the degrees of freedom, which is 2. Our chi-squared statistic is 16.11, and look for it in the chi-squared distribution table, which is table D. Now you'll notice that the largest number that you see in the row headed by 2, which is the degrees of freedom, is 15.20. So 15.20 is the last number that you see, and our number falls to the right of it. So 16.11 would have to be to the right of 15.20. Now find the p-value corresponding to 15.20. The p-value is 0.0005 for 15.20 as the chi-squared statistic. But our number is further off to the right of this chi-squared statistic, which we see in the table. So our p-value must be even less than the 0.0005. So our p-value has to be smaller because it's further off to the right. So a p-value this small is strong evidence against the null hypothesis. We don't know exactly what the p-value is, but we know for sure that it's even less than 0.0005, which is a good thing because that would be strong evidence against the null hypothesis. So the p-value for the chi-squared statistic of 16.11 is less than 0.0005, which is way less than 0.05, which is our significance level. So since our p-value is less than 0.05, we have evidence, not only evidence, but strong evidence to reject the null hypothesis, which says that there is no difference in the number of bird strikes when we change the tilt, which means all counts should be equal. So this ends the chi-squared test. So we reject H naught. And our conclusion from the chi-squared test is that there is a difference, because that is our alternative hypothesis, which says that H naught is not true, which means there is a difference in the number of bird strikes when the tilt of the window is changed. However, the chi-squared test will not give us any further details than just saying that there is a difference in the number of bird strikes based on the tilt of the window. However, now that we know that we can reject H naught, we can go back and look at the observed and expected counts from the data that we've collected and the expected counts that we have calculated, and see which category deviates from what is expected. What is the category that has a maximum deviation or any deviation at all from what is expected based on the null hypothesis that all counts must be equal. Now, one way of analyzing the numbers that we have to make further conclusions that the chi-squared test will not allow us to do is to go back and look at the observed percentages as compared to the expected percentages. So first we calculate the percent of bird strikes in each category, and we do that for the observed values and the expected values. Notice that in this table, in the first row, we have the observed percentages. So if you just look at that row, that should add up to about 100%. So we calculate the percentage of counts in each bucket. So the total number of counts is 53. 31 are vertical, so 31 out of 53 is the fraction of the counts in the vertical windows. We multiply that by 100 to get a percentage. So we do the same for all the three counts. So 14 out of 53 times 100 for the 20-degree tilt, and 8 out of 53 times 100 for the 40-degree tilt. So we have percentages instead of counts in the first row. We do the same thing with the expected counts. So in the case of expected counts, we assume that all buckets must have equal number of bird strikes, which makes it 33% for each category. Now we calculate the difference. We look at the vertical windows. We take the difference of the observed and expected percentages. We take the difference for the observed and expected percentages for the 20-degree tilt, and we take the difference for the 40-degree tilt as well. We look at what deviates, so which category in which category does the observed value deviate a lot from the expected percentages, and that would be the vertical windows. And in the vertical windows, the bird strikes are much higher than what is expected because this is a positive difference. Now, if we look at the 40-degree tilt, it is negative, which means that the observed percent is less than the expected percent by 18.24%. So whether it's a positive difference or the negative difference, these are the two categories that show a great amount of deviation from what is expected to be true. So our conclusion based on the chi-squared test is that there is a difference, but further analysis shows that the vertical window has a significantly larger number of bird strikes as compared to the expected number of bird strikes, and the 40-degree tilt category comes pretty close because the number of bird strikes is much less than what is expected to be true based on the null hypothesis. Now, another way of analyzing the data to understand the kind of difference that tilt makes is by just simply comparing the observed counts and the expected counts. See where the deviation is the largest, and based on that, can we make some sort of conclusions. Now, the third and usually the most important way of analyzing the counts after we have rejected or failed to reject the null hypothesis is by examining the chi-squared components. Remember, we talked about how each is called a component because we add them, the three categories, the components of the three categories, to give us the chi-squared statistic. The reason why our chi-squared statistic is so large is because the largest contributor to that large chi-squared statistic is the 10.06, which comes from the vertical windows. So the category that deviates the most from what is expected, which is that the counts are all equal, is the first category of vertical windows. And that's what we see from the chi-squared components. The second one is, of course, the one that comes from the 40-degree tilt. So we can, from further analysis, we can add that the vertical windows do have the maximum number of bird strikes, and tilting the window to a 40-degree level does reduce the number of bird strikes. Now, this is how we would write down the conclusion of our chi-squared test. So first, we use the p-value as strong evidence to reject the null hypothesis, which really shows that there is a difference in the number of bird strikes depending on the tilt of the window. This is where we end with the chi-squared test. But we can add a little more by further analyzing the observed and expected counts after we have rejected the null hypothesis, and our further analysis of the chi-squared components. If you remember, the largest chi-squared component was that which came from the vertical windows. So that helps us add a little more to our conclusion, which says that the vertical windows have much higher bird strikes than windows that are tilted by a certain degree, and tilting the window by 40 degrees would show the least amount of bird strikes. So that's our complete conclusion. The second part of our conclusion really comes from the analysis of the observed and expected components, or rather the observed and expected values, and from the components of the chi-squared statistic. But the chi-squared test is really only telling us that there is a difference and not giving us any more specific details.